Every story of exploration begins the same way, with a species that looked up and refused to look away. We did not evolve for space. We evolved for savannas, for rivers, for the warmth of fire, but somewhere in the human brain, a restlessness took root. In 1961, a 27-year-old Soviet pilot named Yuri Gagarin sat inside a metal sphere barely large enough to contain him and rode a column of controlled fire into the unknown. 108 minutes later, he returned. He said the Earth was blue, beautiful, and small. 8 years later, Neil Armstrong stepped onto the surface of another world. 600 million people watched. The entire species held its breath. We had done the impossible, and then for 50 years we stopped. But something changed. A new generation looked at the rockets we threw away after one use and said, "That is insane. What if we could land them back? What if we could fly them again? And again, and again." Reusable rockets did not just cut the cost of space travel. They obliterated the old logic entirely. Suddenly, space was not a government program. It was an industry. A race, a gold rush with no map. And we are just getting started. The moon is 40 hours away by rocket. It has water ice at its poles. Water means drinking. Water means oxygen. Water means hydrogen fuel. The moon is not just a destination. It is a gas station, a laboratory, and a launching pad for everything beyond. The first permanent lunar base will not feel like science fiction. It will feel like a construction site. NASA's plan for these lunar bases unfolds in 3 phases. Mapping and early access through the late 2020s, construction of initial infrastructure and a power grid in the early 2030s, and a semi-permanent human presence established sometime after that. To supply power through the lunar night, engineers are developing a small nuclear fission unit capable of generating 10 kilowatts of continuous power, roughly what an average home on Earth uses in a year. Before astronauts arrive, robotic landers under NASA's Commercial Lunar Payload Services program are delivering science instruments and scouting equipment, mapping safe landing zones and resource-rich sites ahead of crewed missions. The base camp isn't built by NASA alone. Commercial companies are contracted to build landers, rovers, and drones, while international space agencies contribute hardware and expertise as part of the broader Artemis partnership. Spacesuit design has come a long way since Apollo, where the rigid suits of the 1970s limited astronauts to a stiff, shuffling gait. Today's exploration suits are built for flexibility, allowing crews to kneel, bend, and work efficiently during long stays on the surface. At the heart of the new suit design are flexible joint systems, replacing the rigid seals of the past. Bearing rings at the shoulders, elbows, and knees allow astronauts a full range of motion, turning what was once a stiff, effortful task into natural movement. The helmet itself has been redesigned for clarity and comfort, featuring an anti-fog coating and a retractable sun shield to manage the harsh contrast between sunlight and shadow on the lunar surface. Putting on the suit is now a faster, more independent process. Astronauts step into a rear entry hatch and seal themselves in within minutes, a major improvement over the lengthy, multi-person suit-up procedures of earlier missions. Mars is the next chapter, not because it is comfortable. It is not. The average temperature is negative 80 degrees Fahrenheit. The atmosphere is 95% carbon dioxide. A solar storm can deliver a lethal radiation dose in hours. And still we will go. Because Mars is what Earth was 4 billion years ago. A blank page. A world waiting to be written. The first humans to land on Mars will face challenges we cannot fully anticipate. They will improvise. They will suffer. Some may not survive. But they will plant something that cannot be unplanted. A second branch of humanity. From that moment, our species cannot be killed by a single catastrophe. Not an asteroid, not a pandemic, not a war, not a dying sun. Getting to Mars isn't just a matter of distance. It's a matter of time. Using conventional chemical rockets, the journey can take 6 to 9 months each way. exposing astronauts to prolonged radiation and the physical toll of extended weightlessness. Nuclear propulsion offers a faster path. By using a nuclear reactor to heat propellant directly, rather than relying on chemical combustion, a nuclear thermal engine can generate significantly more thrust efficiency than traditional rockets, potentially cutting transit time to Mars by as much as half. A shorter trip means less radiation exposure, fewer consumables to carry, and a narrower window of risk for the crew. NASA and DARPA have already tested early nuclear thermal propulsion concepts, viewing the technology as a critical step toward making crewed Mars missions not just possible but practical. The same nuclear systems being developed for lunar surface power could ultimately serve a dual purpose: generating electricity for a Mars base and propelling the spacecraft that gets astronauts there in the first place. Beyond Mars, the solar system opens into abundance beyond comprehension. The asteroid belt contains more iron, nickel, and platinum than humanity has extracted from Earth across all of recorded history. A single metallic asteroid could make every nation on Earth wealthy beyond imagination. Jupiter, Saturn, Uranus, Neptune, each one a world of extremes. Their moons hold oceans larger than all of Earth's oceans combined, sealed beneath ice. Europa, Enceladus, Titan with its lakes of liquid methane and skies of orange haze. And then there are the machines. Artificial intelligence has already changed science on Earth. In space, it will become something more. AI systems will monitor spacecraft in real time, diagnose medical conditions with no doctor present, navigate asteroid fields at speeds no human brain could process. Eventually, AI will not just assist human astronauts, it will travel ahead of them. Scout, prepare, build habitats, so that when humans arrive, they do not arrive into danger, but into a home. This is not science fiction. This is engineering already underway. But what about the stars? The nearest star to our Sun is Proxima Centauri, 4.2 light-years away. At our fastest current speed, the journey would take 70,000 years. Physics as we currently understand it makes the stars impossibly distant. But physics is not finished revealing itself. A wormhole is a theoretical passage through space-time, a tunnel connecting two separate points in the universe that could otherwise be separated by billions of light-years. First predicted by Albert Einstein and Nathan Rosen in 1935. They are sometimes called Einstein-Rosen bridges. The concept is rooted in general relativity. If space-time can be bent by gravity, it may theoretically be bent so severely that two distant points in the universe fold together, creating a shortcut between them, bypassing the vast distance in between entirely. The fundamental problem is stability. Most theoretical wormholes would collapse almost instantly after forming, far too quickly for anything to pass through. Keeping one open would require a hypothetical substance called exotic matter, material with negative energy density that has never been observed or proven to exist. Physicists Kip Thorne and Michael Morris proposed in 1988 that a traversable wormhole, one stable enough to pass through, might be theoretically possible if exotic matter could be harnessed in sufficient quantities. Whether the laws of physics ultimately permit this remains an open question. Even in theoretical models, traversable wormholes present extreme engineering challenges. The throat of a stable wormhole capable of allowing a spacecraft to pass through would need to be held open against enormous gravitational forces, requiring energy on a scale far beyond anything humanity currently produces. No wormhole has ever been observed. They remain a prediction of general relativity rather than a confirmed feature of the universe. Research continues, with physicists exploring whether quantum mechanics and gravity together might eventually point toward conditions where wormholes could naturally form or be artificially created. The universe is 13.8 billion years old. Technological civilization on Earth is 200 years old. That gap, 13.8 billion versus 200, staggers the imagination. Energy is the currency of civilization, and the largest energy source in any solar system has been burning in plain sight all along. A Dyson sphere is a theoretical megastructure built around a star designed to capture the entirety of its energy output. First proposed by physicist Freeman Dyson in 1960, it represents the ultimate energy harvesting solution for an advanced civilization. The Sun radiates approximately 386 septillion watts of energy every second. Earth intercepts only a tiny fraction of that. A Dyson sphere would capture nearly all of it, providing energy on a scale billions of times greater than everything humanity currently produces combined. A complete rigid shell around a star is considered physically impractical. More realistic proposals include a Dyson swarm, millions of individual solar collection satellites orbiting in coordinated formation, or a Dyson ring, a smaller partial structure built incrementally over centuries. But mathematically, a civilization advanced enough would have no reason not to build one. We search for alien signals with radio telescopes aimed at empty sky. But perhaps we are looking for the wrong things. Perhaps the signature of intelligence is not a radio transmission, but an absence. From the dust of the lunar South Pole to the edge of a star wrapped in human ambition, every concept explored here begins with the same impulse: to understand the universe and to reach further into it than the generation before us dared to try. Thank you for watching this video, and for more like this, subscribe to Industrial Origin.